All right, let's talk about 6.5. So 6.5 is about the area of a surface of revolution. And so this is really kind of an extension of 6.4 when we were finding the length of a plane curve, and you'll see why. So first of all, a surface of revolution is a surface that's generated by revolving a curve about an axis. So, for example, you might have this curve, and if we revolve it around the x-axis, then we get this kind of, it's not a solid, it's just kind of a shell, right? So it's a lot like the solids of revolution from 6.2 and 6.3, but it's hollow, okay? And we'd like to be able to calculate the area of these. So I'm just going to go ahead and give you the result. So if f is a smooth non-negative function, so it's positive, right, or 0, on the interval from a to b, then the surface area S of the surface of revolution that's generated by revolving the portion of the curve y equals f of x between x equals a and x equals b about the x-axis is given by this formula here. So here's the surface area, right? So it's the integral from a to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. This portion looks familiar from the previous section 6.4, right? This is the length of the plane curve. Now this other stuff happens because we are rotating the curve about the x-axis, and so you can kind of think of it like a cylinder, I suppose, but it's a cylinder that sort of changes radius at any given cross-section. The radius is going to be different. Well, what is the radius at any given cross-section? Well, it's f of x, right? So in other words, if you wanted to find the surface area of a cylinder, you would do 2 pi times the radius times the length of the cylinder, right? So here's the radius, here's the length of the cylinder. You can kind of think of it like that. If you want a more formal proof of this fact, then you can read the textbook on pages 370 to 371. But that's basically the idea. It's 2 pi times radius times length. And of course, this is if we're revolving about the x-axis. If we're revolving about the y-axis, well, then we would have to say, g of y instead of f of x, g prime of y, and then integrate with respect to y. Okay? So that's all I have to say is by way of introduction, and I just have 2 examples to show you of this, so it should be a pretty short section. So let's take a look at the first one. It says, find the area of the surface that is generated by revolving the portion of the curve y equals x cubed between x equals 0 and x equals 1 about the x-axis. So let's do it. The first step, as usual, is to draw a picture of this scenario. So y equals x cubed. But only between x equals 0 and x equals 1, right? So let's say x equals 1 is right there, and we want to revolve this about the x-axis, so maybe I should make this a little bigger. But y equals x cubed goes through 0, 0, and it goes through 1, 1, and it takes a curvy path to get there, almost like a parabola, but even more like steep, I guess. So that's what that portion would look like. Of course, on this side of the graph, it kind of goes down, right? So you get this kind of snake-looking thing. But this is the portion that we're interested in, between x equals 0 and x equals 1, and we want to revolve that about the x-axis. So what we end up with is something that looks maybe something like that. Kind of sort of like a little cone, but it's hollow, right? So this is not a solid, it's just that little hollow shell, right? Okay. Well, so let's see if we can find the surface area. So the surface area here is going to be the integral from a to b, that would be 0 to 1 in this case, of 2 pi times f of x. This was the curve y equals x cubed. So f of x is x cubed, okay, times the square root of 1 plus f prime of x squared. So let's see, if f of x is x cubed, then f prime of x is 3x squared, right? So this would be 3x squared squared. Okay. So let's see what we get. Well, first of all, we can take the 2 pi out. And then we've got an x cubed times the square root of 1 plus 9x to the 4th dx. And that's set up nicely for us to do a u substitution. I'm going to let u be 1 plus 9x to the 4th, right? And so then du would be 36x cubed dx. Okay, so I don't have a 36x cubed, but I do have an x cubed. And I can force it to be a 36x cubed, right? As long as I offset by a 1 over 36 there on the outside. Okay. Now, while I'm at it, I can go ahead and change my limits of integration, right? So I can say when x equals 0, u equals, it looks like it's going to be 1. When x equals 1, u is going to be 10, right? So it looks like, so I've got 36x cubed dx. That whole thing's going to be replaced with a du. This thing is just going to be replaced with a u. So it looks like I've got, now 2 pi over 36 would be pi over 18. So I've got pi over 18 times the integral from 1 to 10 of square root of u du. Well, that's pretty simple, right? So square root of u is u to the 1/2. So this is going to be 2/3 u to the 3/2. So 2/3 u to the 3/2, and we're going from 1 to 10. Oh, that is not nice at all. If it were from 1 to 9, that would make me feel a little bit better. But, oh well, I guess beggars can't really be choosers here, right? So, I don't know what that's supposed to mean in this context, but anyway. Well, yeah, so we're not going to get a nice looking answer. This is going to be pi over 18 times, if I plug in 10, gosh, square root of 10 is not nice at all. It's just going to be 2/3 times 10 to the 3/2. Minus, if I plug in 1, well, that works out a little bit more nicely. That's just going to give me 2/3. I suppose I could factor out the 2/3, right? Cancel the 2, that leaves a 9, and then 9 times 3 is 27. So I guess you could get pi over 27 times 10 to the 3/2 minus 1. That's about as good as you're going to get it in terms of getting a nice answer. If you want a decimal approximation, you could pop that into your calculator and see about how much that is. So let's do that. Pi over 27 times 10 to the 3/2 minus 1. So that's about 3.56. Okay. By the way, if you ever do any rounding, you need to use approximate signs. Don't say that this equals 3.56 because it doesn't, right? They're not equal. But they're approximately the same. Okay, so there's the first example. Second example says, find the area of the surface that is generated by revolving the portion of the curve y equals x squared between x equals 1 and x equals 2 about the y-axis. Okay, so we're going to go, we're going to revolve the other way, but we've got y equals x squared. So y equals x squared. This time we want to go between 1 and 2, between x equals 1 and x equals 2. So okay, x squared goes through 1, 1, and then it goes through 2, 4, right? And it's a parabola looking thing, but this is the portion of the curve that we're interested in. And now, I didn't really leave myself enough space to draw it, but we're interested in revolving this thing about the y-axis, right? Oh, what was I trying to do there? Anyway, we're interested in revolving it around the y-axis. So, if I were to do that, and now, let's see, I've gotten myself into trouble, but, you know, we get something along these lines. Right? Something like that. Okay, so now because we're revolving around the y-axis, I think I'm going to have to take everything and solve it for x, right? So in other words, this was the curve y equals x squared. Well, that implies that x equals the square root of y, right? So we've got x equals square root of y, and that's going to be, if we take any given cross section of this, like let's say, you know, we take this cross section here, what's the radius going to be? So if this is y, then the radius is going to be the square root of y, right? It's going to be x, which is the square root of y. Okay, I think we're ready to set this thing up. So the surface area S. Surface area S. We're going to integrate with respect to y, so we're going to go from y equals 1 to y equals 4, right? So we're going to go from 1 to 4 of 2 pi times g of y times the square root of 1 plus g of y squared. Oh goodness, I always forget to do this scratch work, so let me do it now. If g of y is the square root of y, or in other words, y to the 1/2 power, then g prime of y is 1/2 y to the negative 1/2. Or if you like, you can call that 1 over 2 root y. Okay, so we're going to have 1 over 2 root y squared dy. Okay, ooh, all right. Well, this doesn't look so good right now, but I bet it'll clean up nicely. Let's see. Let's see how this goes for us. So we can take out the 2 pi. When you multiply two square roots, you just multiply the radicands together. So I know I can move this y inside of that square root, so that's not a huge deal. And and when I square this one, you know, it's not that bad either, because this is just going to be what, 1 over 4y. 1 over 4y. Okay. So this is going to be the square root of, now if I move this y in, I'm going to get y plus, so this is 1 over 4 times y. Then when I multiply it by the other y, I'm going to get y over 4 times y dy. Well, that's not bad at all. That's just going to be 1/4, isn't it? So this is 2 pi times the integral from 1 to 4 of the square root of y plus 1/4 dy. Okay, so I think that's pretty straightforward to solve at this point. We can just let u be y plus 1/4. right? And then du is going to just be dy. And that's all there is to that. I suppose we'd have to change our limits of integration. Oh, man. Those were nice limits of integration. Well, okay, that's fine. So when y equals 1, u equals 5/4, right? When y equals 4, u equals, 16/4 plus a fourth, so 17/4. And so we get 2 pi times the integral from 5/4 to 17/4 of square root of u du. So that's 2 pi times 2/3 u to the 3/2 from 5/4 to 17/4. How nasty. That's not fun at all. Okay. Goodness gracious. Do we have to do this? I suppose, maybe if we had pulled out the 1/4 up here, like we could have called this 4y plus 1, right? And then the square root of 1/4 is 1/2, and the 1/2 times the 2 pi would just leave a pi. That might be a little easier to work with here at the end. But I mean, at this point, it's just numbers. I mean, let's just get to it. It might have been easier to pull out the 1/4 up there, but anyway, not a big deal. So we're going to have 2 pi times 2/3. I guess I could take out the 2/3 though, couldn't I? So let's take out the 2/3. That's 4 pi over 3 times. And then you're just going to have 17/4 to the 3/2 minus 5/4 to the 3/2. Okay. And at least, I mean, square root of 4 is nice. Square root of 4 is 2, and then 2 cubed is 8. So they're both going to have a denominator of 8, which you could pull out as well. 8 would cancel, or 4 would cancel 4 and leave a 2. So I think it would just be pi over 6 at the end of the day. Pi over 6 times 17 to the 3/2 minus 5 to the 3/2. But again, that's about as nice, I think, as you're going to get that. You can plug that into your calculator to see about how much it is. So pi over 6 times 17 to the 3/2 minus 5 to the 3/2 is about 30.85. Okay, anyway, and that's that, right? So that's all I have to say about this section.